Okay, the chips are down, right? Coming into the home stretch here. We've got two, these are sort of extra credit optional material lectures. I may not even do the second one. I mean assignments. Assignment 15, there's also an assignment 16.
Yeah, you should upload both if they're extra credit.
May not lecture on that, but and the thing is, I'm doing these a little differently. I was going to experiment, so you might not want to start these right away. So what I plan to do for these two extra credit ones is set up quiz questions, like the quizzes we've been doing with those problems, and so with different numbers, because some people treat these like really elaborate extra credit certificates that they write out for themselves. They just copy the solutions and they hand them in and they get extra credit points, which I think is kind of stupid. And it kind of undermines your learning. So the quiz is going to have these questions on it, which if you're going to do the quiz to get the extra credit points, you got to at least go through the steps with different numbers and get the right answer.
So will they be, it's an assignment grade then, and extra credit for assignment grade?
It will be an extra credit assignment grade.
Okay.
Yep.
And it'll just be all of those questions?
It won't be, I won't have time to do all of them, but I'm going to pick like 3. So I'm not sure which ones yet. And I'll probably put a star and some extra notes on here when I have it all straightened out.
Will those be timed?
Will they be timed? I'm not sure. Good question. Probably not.
Okay.
So the test next week is going to be on material up to last week, right?
12, 13, and 14 assignments.
Okay.
Yep, 3 assignments. And hopefully I'll be able to talk for the rest of the lecture today. Yeah, so this is actually, and I ran out of Amelito's material, so I had to go back and access my old material. You can kind of see, you can get a flavor of how lectures used to be. Amelito has this really, I like his technique of he just really simplifies things to the essentials. I have a lot of extra stuff here, which has some good things too, but it makes lectures a little bit longer. So today we're going to move into the start of the cool stuff. So this whole class, circuits is actually pretty awesome stuff. You can do a lot with circuits, but if you're in the double E path or mechanical path, what comes next after circuits kind of covers the higher level systems involving these things. And frequency response is sort of our way to kind of get into, kind of dip our feet into the water of that. And tomorrow's lab that's going to be the theme for tomorrow's lab too. We're going to be measuring the frequency response of some networks. We're going to be doing this LED pulse detector circuit, which requires amplification and filtering to get the right, a nice clean signal of our pulses. And in a nutshell, frequency response is the point that, all of these components have omegas in them now, L's and C's anyway, and when you make a circuit, it has a frequency-dependent behavior. You change the frequency, and you get a different response. Also, like I said, things start being broken down into systems with, where you have subsystems, and here's the sort of thing where you have sort of like an input force going into some system. And with the frequency response, now this is actually for a mechanical system, and what's cool about this stuff is that the mathematics is the same whether it's a mechanical or electrical system. And you represent the frequency response by what's called the system function, a function of omega. And what that means is in the time domain, if you give it a square wave, and you run that through this frequency response. Well, the square wave has a spectrum. You know how they're doing like Fourier series? Are they doing those in your differential equations? They did them already, right? Fourier series. Did they say how in diffie qs? Yeah, they did Fourier series, right? No? So I thought somebody mentioned Fourier. Maybe it was Jeremy. Really? Physics, maybe? Kind of sounds familiar. Well, did they take like a square wave and say you can break that up into the sum of sine waves? of different frequencies? Well, you can't. So this square wave has a fundamental frequency of 1 period, which is like, say, this 1 hertz, and in order to because it's 1 second to go a complete cycle, that means 1 hertz. Yeah, but in order to get the square wave, you have to add up components at like 3 times the frequency. That's called the 3rd harmonic, the 5th harmonic. These are 5 times the fundamental frequency, 7, 9. You add up a whole bunch of odd harmonics like this. It's a mathematical typical function to get a square wave. And what happens is you run it through a system where you have a filter that emphasizes the components in this frequency band, and in other words, between like say 5 and 9 hertz. And what happens on the output is, I don't know why this is so big, but you can see you have an amplification in this region because of your system, and the output looks like this. You can see these components have been changed relative to each other, and that's actually not terribly compelling. But this is actually sort of like this would be considered a resonant circuit, and I'm going to bring in that Tibetan singing bowl that James got me a while ago, and a resonant circuit kind of like rings at a certain frequency. And you get mechanical resonances as well. And so what this is sort of showing you is, this input signal has components at a lot of different frequencies, but at the point where you hit the resonant frequencies, those things get amplified pretty significantly on the output. And why does that matter? Have you heard of the Tacoma Narrows Bridge?
Yeah, that's the one that fell down, right?
The one that fell down, and there was they called it Galloping Gertie, I think. And this is footage. And this is after they built this bridge, brand new bridge. They didn't really understand this thing. It was a new effect of like flutter, that the wind blowing up and down the channel there caused the whole thing to start fluttering, and that proved to be pretty fatal for the bridge. And a frightened dog that was trapped in a car on the bridge after the owner had fled. And they tried to rescue it, but the dog kept biting people because he was so freaked out. And the whole thing collapsed in the river. So,
why would the owner think that it would be quicker to get away on foot than just finish driving across?
Probably the way it was shaking. I don't know. The whole thing might get flown into the river. I don't know. So that's Tacoma Narrows Bridge. It eventually collapsed, and yeah. So this also happens in electrical circuits. You can get resonance effects as well, and then mechanical systems. This kind of shows you some of the analogs between electrical and mechanical systems, which looks like a lot of mathematics, but here they show you like conversion from electrical to mechanical. Here you have RLC sort of thing. What they've got is they've got like springs for no, what is that? No, that's a damper for the resistor, and a mass. I don't get that, but you can see what they're trying to do. They're trying to show you the effective mechanical system that has the same sort of mathematical effective behavior as the electrical circuit. So the point is, if you're a mechanical engineer, we have a lot of those here. If you're a civil engineer, right, you might be designing a bridge, making sure it doesn't have that kind of resonance is also pretty important, as well as for electrical engineers. And the fundamental part of the frequency response is we identify that as by this thing called the transfer function h of omega, and it's a ratio of some phasor output divided by some phasor input, and this could be a voltage or a current on either or. Whatever you choose it to be, it's whatever the output phasor is divided by whatever your input phasor is. That determines h of omega, which has a magnitude and a phase angle like we've been working with so far. You could do a voltage gain transfer, which would be just the ratio of the output to the input. It could be a transfer impedance, which is the output voltage to the input current. It could be a current gain. It could be a transfer admittance. Normally we look at these, we normally just look at the voltage gain. So in example 1, we're going to look at a circuit and determine its frequency response. And this is on your handout. If you came in late, there's a handout right up here. And you know, it's not terribly complicated at this point. You have a voltage divider circuit, if you've noticed here. If you want to know what VO is, to some, or phasor VO to some phasor input VS. You know the element of the capacitor has an impedance of 1 over j omega c, and it has you've got this R here, so you just basically use the voltage divider formula to find VO as VS times the impedance of what you're measuring across there, your VO, 1 over j omega c, over R plus 1 over j omega c. And you go ahead and multiply top and bottom by j omega c to get rid of the fractional part. And what you end up getting is that these things cancel, and then that this also cancels with that. So you get that our h of omega, our frequency response, our system function is VO over Vs. And that's going to be 1 over 1 plus j omega RC. And if we let some omega 0 equal 1 over RC, you can write this in a more standard form as h of omega equals 1 over 1 plus j times omega over omega 0. It's a little awkward, though, still to kind of have that rectangular form in the denominator, so we can convert this to polar. And say, well, let's think of this as, let's think of this as the magnitude, which is going to be 1 plus 1 over 1, the square root of 1 plus omega over omega 0 squared, with an angle of the arctangent of omega over omega 0. So the overall thing is that you have a magnitude of 1 over square root of 1 plus omega over omega 0. And a phase angle of minus, because we're going to move that back up to the top, arctangent of omega over omega 0. So that is the magnitude, and this is the phase. Okay, so those are all functions of omega, and we can explore what the transfer function is going to do at different frequencies. So suppose omega equals 0. What is our response going to be when omega equals 0?
It's 1, right?
Yeah, it's going to be 1 with an angle of 0. And, well, what about when omega equals infinity at really high frequencies? H of infinity is going to be what? 0, because that's going to dominate. That thing's going to go to 0, but it's going to have an angle. What's the angle going to be?
90.
It's going to be negative 90. Yep. Well, it doesn't really matter if it's 0, but It's going to approach that with a negative 90-degree phase shift. And what about when omega equals omega 0? Well, you're going to have 1 over 1 plus j, right? And that is going to be the square root of, oh, by the way, I didn't really, there's an omega over omega 0 squared here, right? So that didn't really show up. So that's going to turn out to be 0.707 with an angle of minus 45 degrees. And we call this a low-pass filter. Why? Well, low frequencies, it has a response close to 1, so it's going to weight frequencies that are low around 1. It's going to let them kind of go through unchanged. But high frequencies, it's going to weight by a really small number as h of omega approaches 0. You can plot out the transfer function. It looks something like this. So you can kind of see the nice curve here. You can also see how the phase angle is changing. And this point here is our omega 0, which we also call it's called the cutoff frequency. Sometimes it's called the corner frequency. But it's a special point on the curve which sort of indicates, beyond this point, things are dropping off kind of rapidly. Above that point, things are close to 1. So we consider this this is considered the pass band because the transfer response is close to 1, and this is considered the stop band or the rejection band down here, where we're kind of suppressing the frequencies beyond omega 0. So right. So in other words, if Vs is cosine of and maybe like omega 0 over 100t, right? Then VO is going to be, approximately the same magnitude because your frequency is 1/100th of omega 0. So you're like way down here, close to 1, right? So it's going to be approximately, cosine of omega 0 over 100t. And maybe there's a little phase shift, but there isn't even hardly much of a phase shift at all, right? But when your input is cosine of omega 0, right, your output is going to be reduced a little bit. It's going to be like 0.707 cosine of omega 0, and there's going to be a phase shift of minus 40 degrees, 45 degrees. So different frequency phasors are going to be treated differently. Example 2 shows you the transfer function of an RL circuit, and again, you're in a situation, well, this becomes, j omega L, and you have another voltage divider, so V0 equals j omega L over R plus j omega L times Vs. So again, our h of omega is VO over Vs, which is j omega L over R plus j omega L. Divide that by j omega L, top and bottom. And what you get is that this equals 1 over 1 plus r over j omega L. So it's a little bit of massaging, and again, we can let omega 0 equal r over L. And that tells us then that our h of omega is going to equal 1 over 1 minus j omega 0 over omega. A little bit different now. The omega is below instead of above. And in polar form, you know, you do some extra work here, and you get it's going to be, let's just kind of cut to the chase, it's 1 over the square root of 1 plus omega 0 over omega squared with an angle of, and that's going to be the arctangent of omega 0 over omega. Now, this can be also written as 90 minus the arctangent of omega over omega 0 if you don't like having your variable omega in the denominator. And you can kind of, again, explore this. H of 0, when omega is 0, what do we got here since we got a denominator of omega there? Dividing by 0 makes this whole thing really big, so the whole thing is going to be 0 with a, that looks like a angle of 90 degrees. And h of omega 0 is going to be 0.707, in this case with an angle of plus 45 degrees. That's the cutoff corner frequency. And h of infinity is going to be 1 angle 0, right? Because when omega is infinity, this denominator goes to 0. I mean, the denominator of this omega 0 over omega goes to, this thing goes to 0, and the denominator goes to 1. And any guess what we might call this device? What kind of filter? It is a high-pass filter. It's going to allow high frequencies to get through, and it's going to block low frequencies. And again, the transfer function looks like this now. So it's it has a suppression effect when you're below omega 0, and it has an allowance effect that allows things to go when omega is above omega 0. This is the basis of filtering audio signals as well in your phone, in your stereo. Very useful. Comes up in so many circumstances. You might be given some random combination of R's and C's, and you can solve that. It's really just a question of kind of finding things in the right form. This is kind of a grinding one. I don't know if you find this very interesting. Let's just sort of set it up. You know, to set this up, you would say, well, okay, so H of C, or ZC, is going to be, 1 over j omega c. We tend to keep things in their ratios rather than putting the j on top. Z parallel, which is going to be the combination of these guys. And we can call this guy, it can be a little easier to put variables in for these guys, even though they're given values here. It's just sort of easier to keep the symbols straight in some ways than messing with all these numbers. If we call that R1 and this R2, and we call this a C, then we have a ZC, and our Z parallel, it can be kind of messy. It's going to be R2 times 1 over j omega c over R2 plus 1 over j omega c. which can be reduced as R2 over 1 plus j omega R2c. And then, once again, you have a voltage divider where V out equals V in times our parallel combination there over the R1 plus ZP. And you can continue to crank that out, and eventually you'll get that it's 1,000 over j omega plus 11,000, which, when you examine this, it will sort of appear like a low-pass filter. If you are interested in making a plot of something like this, you can use Wolfram alpha, which is a pretty convenient way to do that. And this slide shows you all about how to do that. This is what you actually type in. You're going to use the ABS function for the magnitude, so you can plot the absolute value, and 100 over I omega plus 11,000. When omega goes from 0 to, say, 100,000 radians per second, right? And what's great, it'll actually display that for you, so you can really show the behavior, and you can even identify the cutoff frequency. It's going to be like 0.70, so it's going to be something like around here. That's going to be your omega 0, something there. And you can also plot phase in case you needed to. You can also do this, of course, in MATLAB. And just be aware you have to kind of get phase in degrees. So the arg function finds phase in radians of a complex number, and then you convert it to degrees over the same interval. You get something that looks like that. And again, in MATLAB, doing the same thing. You get a little more control in how you set this up. You can also do a semi-log x function, meaning you can compress the horizontal axis to kind of give you a better sense of a broader many orders of magnitude. Anytime you're going over several orders of magnitude in a variable, it can kind of be helpful to use a log scale. And this shows you what that looks like on a log scale. And again, your omega 0 is going to be like somewhere like around here. Typically, with these filters, when you're at omega 0, you're at an angle of 45 plus or minus, so that's going to be effectively your omega 0. Omega 0 is the part where it's the frequency. It's the frequency where the real and imaginary parts have the same size. They have the same magnitude. They could be opposite in sign, but they have the same magnitude. So they actually have about the same amount of effect. You know, you go into the pass band, the imaginary part kind of takes over. I mean, you go into the stop band, the imaginary part takes over. As the imaginary part gets really big, things kind of drop off. At least relatively speaking here. I don't know if it's not always going to be imaginary in the stop band, but you can also do these things with op amps. We're going to be playing around in the lab tomorrow with an op amp. This is considered an active filter. When you combine filtering with some amplification, again, you have a 1 over j omega c. You have a feedback impedance, which in this case is just, we can call this R. You've got the same R over here. You can call this your source impedance, right? And this is an inverting op amp, right? So, And we know the gain of an inverting op amp is, again, that's V out over V in, if those are phasors, and that's going to also be the same thing as H of omega. And that's just minus ZF over ZS. And just setting up, the basics, not to spend too much time grinding through the stuff, it's going to be minus R over, again, R plus 1 over J omega C. Which isn't really giving you much amplification, but you could provide more amplification if you change the gain of that thing. And ultimately, the output voltage, steady state, when the input voltage is blah, blah, blah. So your ultimate H of omega is, in the circuit, is 1 over J omega 0 over omega minus 1. And then they're asking you to find, what's the output voltage sinusoidal steady state time waveform when the input voltage is 1 cosine of 100t versus 1 cosine of 10,000t with a 90-degree phase shift. And what you would do is just plug in the values of your phasors, right? So when omega equals 100 radians per second, that's your V in. And your V out is just going to be your V in times the system response at the frequency of your input phasor. So again, just kind of showing you how that works. You plug in 100 for your H of omega, plug in omega of 100, and you're going to take your input phasor 1 angle 0, and you're going to times that by your system function, which is 1 over J times. And in this case, oh, by the way, the omega 0 is 1 over RC, which is, if you plug in those, it's going to give you 10 to the 4th radians per second. Because your R is 1,000 and your C is 0.1 microfarads. And so you plug in, all right, you got to do omega 0 over omega, so that's going to be 10 to the 4 over 10 to the 2, which is omega, minus 1. This whole thing, the ratio there is parenthesized, but not the whole thing. And so that equals 1 over J 100 minus 1, which is approximately minus J over 100. So that's your phasor output, so that therefore your V out as a function of time is going to be something like 0.01 cosine of 100t minus 90 degrees. And then if you do that at 10 to the 4 radians per second, in this case, your and your V in, by the way, is one angle 90 degrees. Then your V out is going to equal your V in, again, times the system function, 1 angle 90 degrees, divided by, in this case it's J times 10 to the 4 over 10 to the 4. You're actually hitting it right at that corner frequency. And so that equals 1 angle 90 over root 2 with an angle of 135 degrees. So that's 0.707 with an angle of minus 45 degrees. And that means your V out when you're at that frequency is going to equal 0.707, and cosine of 10 to the 4t minus 45 degrees. Oops. So again, you're hitting this thing at two different frequencies, and this is where we can really capitalize on this frequency sensitivity now by using it to kind of sculpt the waveform that we're putting in it, and giving us a different waveform on the output. Yes, James?
So maybe I missed something fundamental at the beginning, but what's the difference here between this and what we've been doing?
What's the difference between this and what we've been doing is it's really just focusing on this this system function h of omega as a way of describing the behavior of the system at all frequencies.
H of omega is just going to be one voltage over the other, or? Yeah,
it's the ratio of the output to the input.
Okay.
It's kind of like the gain of an op amp, but it's got a frequency component in it now.
Okay.
And it doesn't necessarily apply just to op amps, it applies to everything. Yeah. So every time you adjust the the equalizer on your stereo or your phone, where you can shift the frequencies up and down, you're messing with a filter and you're changing the amplitude gain on that particular filter. But that's a filter that's selecting, it's passing frequencies at a certain frequency and it's rejecting other ones.
Okay, it's the ratio of the input to the output.
H of omega is the ratio of it's the output divided by the input.
Okay.
Yep. It's kind of, it's very similar. It's using it. It's being more symbolic and less numerical, so that we can see what's happening over many omegas instead of just finding it at one frequency. We're kind of extending this over many. And again, here is the. I always like to visualize these things, right? Because when you're just talking about 1 over j omega 0 over omega minus 1, where that's 10 to the 4, that's a little hard to visualize, right? So what if you take in MATLAB and make an omega vector that goes from 1 hertz to 1,000,000 hertz, right? And if it's we construct our system function by saying, okay, we're going to divide this by here's our omega 0 divided by omega minus 1, and on a log scale on the x-axis we can plot omega and the magnitude of the system function, right? So it tells us, again, you take this thing, so you're hitting this thing with a frequency of 100 hertz. You look at the system function and you identify, well, here we are at 100 hertz. Well, my amplitude is pretty small there. And it's telling you that, yeah, you're only going to get 0.01, an amplitude gain of 0.01, suppressing that thing, right? If you hit it with a signal at that frequency. But if you're hitting it a signal with a frequency of 10 to the 4, you're going to get, it's going to get all the way, it's going to get, 70% of the energy is going to get through, or 70% of the voltage. So this brings us to resonance, which you're gonna have some homework on, and I was trying to come up with I was taking that Tibetan bowl and trying to see if I could somehow if you hit it at the right frequency with a sine wave, can you get that thing to ring? And I couldn't get it to work. But I am going to show you, if you whack it, you can see the thing oscillating at the resonant frequency on the scope. You can actually pick up that thing and actually see it, which is pretty cool.
Do you do that with the tuning forks too?
Yeah, it's the same idea as a tuning fork. And, you know, the energy is kind of shifting back and forth, but it's kind of self-propagating at that resonant frequency. And if you could take a circuit, just an LC circuit, and supercool it, so it becomes superconductive, there's no resistance, then yeah, if you hit this thing with an impulse or whatever, it'll just start ringing essentially forever. So it will just, because there won't be any energy loss at superconducting temperatures, it will just oscillate back and forth like an oscillator.
Can you do that?
No. No, but we are going to build some bandpass filtering on that LED detector and get a sense of how that, you're going to get to design the filter, do a little bit of filter design to try to optimize the response. You can get a nice clean waveform on the output. But resonance is something that the outcome this class has, so it's a desirable understanding that you get exposed to this before the class is over. So the thing about resonance is when you have two energy storage devices, they can actually create the situation. It's essentially like a bandpass filter, but they can actually, they'll resonate, they'll ring at certain frequencies. And the resonant frequency, in this case, it takes place when the capacitive ZC and the inductive ZL are equal in magnitude and opposite, thereby resulting in a purely resistive impedance. So if you take this circuit and you say, well, okay, I've got a ZL here and a ZC here, and if I look at my total impedance here, I've got a Z as R plus J times omega L, right? But I also have a minus 1 over omega C because of that capacitor, right? And, well, interesting, yeah, these things are, you can't make these things go away, but they're having a tendency of sort of canceling each other out, right? Because this one's positive and that one's negative, right? What happens if you choose an omega 0 such that, omega 0 times L equals 1 over omega 0 times C? Well, you'll find this familiar value that, well, if omega 0 happens to be 1 over the square root of LC, which is that same omega 0 we found for the step response, or the F0 equals 1 over 2 pi times the square root of LC, what happens is you have the least amount of impedance to the current flow, so you'll get the most current flowing through the circuit when you have it at that frequency. You get the highest response there. The impedance is purely resistive in that case. The supply voltage Vs and I are in phase, which is interesting. So the phase angle is going to be 0 between them. And the magnitude of the impedance is at a minimum. So it has the least resistance to current. And the other thing is, though, that the inductor voltage and the capacitor voltage can be much more than the source voltage, because you still are getting a VL and a VC here. But because of the relationship, they're equal and opposite, so the VL plus VC, they sort of cancel out. But they can be really big. So when you're working on a resonant circuit, you kind of have to be careful, because you can actually build up really large voltages that could shock you if you touch it at the wrong point. Nothing that we're going to do in the lab is going to be dangerous, unfortunately. But in other situations, you might run into problems. The other problem, though, is that the inductor itself has a little resistance in it, so you can't quite, unless you supercool it, you can't get the really, really powerful resonant effects. Yeah, so that's the little bit, and the frequency response of the resonant circuit is, in this case, in general, right? This is for any particular omega. You're going to get, well, if your I is this, and your I is going to be the magnitude of I is going to be your phasor Vm over the magnitude of the impedance, which is going to be R squared plus the square root of the complex of the imaginary part squared. And the average power absorbed by the RLC circuit is going to be 1/2 I squared R. That's the real power. And the highest power that you can dissipate is going to be at the omega 0 point. That's the maximum current you can get, Vm squared over R divided by 2. So at the resonant frequency, you're getting the most power out of that resistor as well. A lot of stuff here, it's kind of just, you know, if you're going to do the homework, you can kind of just pull this up in the book and follow along, or just pull these slides up if you want to. But of interest are these, again, these 0.707 points, where the response is 70% of the peak value. We call these the half power frequencies because since power is related to either the square of the current or the square of the voltage, when you square 0.707, you're going to get 1/2, right? So you're basically getting half the power at these points than you are at the peak. And so that's another word for those frequencies. And you set the impedance Z equal to the square root of R, and that gives you a way of solving for these two frequencies. Because when you square Z, then you're going to get Z squared is going to be 1/2 of R squared. Anyway, this helps you find these guys. And these define the the bandwidth of your frequency response. So this is telling you the pass band. Again, if you are designing an equalizer, you know, you really like the frequencies from like, maybe you want to emphasize your bass frequencies. You can get really big, you know, you get these cars that have these giant bass amplifiers that provide like mini earthquakes when they drive by, right? So they've chosen the omega 0 to be like, 100 hertz, you know, these really low rumbling frequencies, and you know, you choose the bandwidth to be whatever you want. If you want to just emphasize the low frequencies, you can make it really tight, or you can make it broader if you want to include more. And then you amplify the heck out of it, right? So it just goes, right? And you know, if your plates start to rattle in your house, what is that an indication of when the car goes by? Resonance, yeah. It's hitting like a resonant frequency that's really good frequency for that thing to kind of pass through the ground and, you know, get everything shaking. I was actually thinking this would be, you know, I was like, God, if I can feel those cars all the way out in the street, maybe I can do something like that for the gophers in my backyard. Just get a really big power amplifier.
You should trick out your electric car.
And bury it in the sand and just drive them crazy, right? This is what engineers think about, you know, when Harley Davidsons and other loud vehicles drive by. Yeah, so, but there's another interesting factor, and we're kind of running out of time. We can pick this up, but the Q, briefly, is the Q is kind of like showing you like how selective, it's sort of like the quality factor, and it's the ratio between the peak energy stored divided by the energy dissipated in one period. And you know, if you have just a little bit of a shallow peak, that's a really a low Q value. It has to do with the ratio of these guys. You can see that having a small resistance is going to give you a bigger Q. And other than that, it's a little bit hard to kind of figure out how you're going to get a big Q. But the sharper and the bigger the Q, the more selective it is, and the more of a magnification you get at that resonant frequency. So they're more dangerous, you know, when you're hitting it at right the resonant frequency, they're going to have really high voltages building up in them. Yeah, so anyway, we can kind of look a little bit more at this on Wednesday, just kind of casually exploring these sort of things.
This is on.